In this session, we're going to cover the bisection method, which is a method for finding the roots of a function. So if we got some nice axes up here, and someone gave us the function f of x, and they said between the 2 points, xa and xb, they suspected that there might be a root. And the reason that they suspected this is because they found f of xa to be negative and f of xb to be positive. Now, that doesn't guarantee that you've got a root between them, but it's a good clue that there might be. We might guess that the function was something like this, okay? And therefore, what we're trying to look for is this root here. So the bisection method is one of a whole host of possible methods you could use to find this root, and they vary in complexity and efficiency. The bisection method is possibly one of the conceptually simplest methods available. And as the name suggests, what you're doing is just picking a domain and bisecting it. So you're cutting it in half every time, and you keep trying to narrow down the domain in which your root could be. So at the start of the method, what you do is you pick xa and xb such that they've got opposite sign. Doesn't matter which order, positive, negative, or negative, positive. And you evaluate the function f of xa to find this point's value, and f of xb to find the value up here. And then once you've got those pieces of information, you begin this 4-step method. So the steps are, number 1, find the midpoint between xa and xb, which is just going to be xa plus xb, divided by 2. Okay, simple enough. So that will give you our first new approximation, which we can call x1. Obviously, the next time through, this is an iterative process, so we repeat it. The next time through, we'll call it x2. So in general, we're going to call this point xn. Okay? The second step, once we've found that midpoint, is to evaluate f of xn. What is the value of our function at our new bisected point? Okay? The third step is, if this new approximation is good enough, i.e. if f of xn is very, very small, i.e. very, very close to 0, or if the new range we've got is sufficiently narrow for our application that that's okay, then we'll stop. So if good enough, stop. Stop. Okay? And the fourth step, and this is the sort of slightly clever bit, is you have to then say, I've got 3 points. I've got xa, I've got xb, and somewhere between the two, I've got x1. And you have to now work out whether the root is on the left-hand side or the right-hand side of x1. And we do that by comparing the sign of f of xn. So we say, okay, if our new point, in this case, it's going to be very close to the root, our new point's in the middle there, and we draw a line down, this is a negative value. So we've got f of xa, it's negative, we've got f of xb, it's positive, and we've got f of x1 now, and it's negative as well. That tells us that the root must be on the right-hand side, okay? Because we still need to have a sign change between our two evaluations of the function. So what we have to do now is just choose new domain, okay? And those are our 4 steps, and we just keep doing that and repeating it until we're happy and we eventually exit the loop by satisfying this thing here. So what we're going to do is we're going to keep the method up on the board here, and we're going to work through an example. So the example we're going to look at is a simple polynomial f of x, our function, equals minus 3x cubed plus 7x squared, and then we've got plus 2x minus 4, plus 2x minus 4, and the question is going to give us our 2 initial guesses. So the ends of our domain are going to be that xa equals 0.5 and xb equals 1.5. So taking these pieces of information, we've got a little bit of work to do before we can get into the loop. So what we're going to do is, for a start, just draw some axes up here. Okay, and we're guessing at this point. So the only piece of information we've got is that we've got an xa here at 0.5, an xb here at 1.5, and we now want to evaluate the function at those 2 points. So what we do is we just chuck it into the function. So f of xa equals, so we put 0.5 in wherever we've got an x, and that gives us a value of minus 1.625. Okay, and f of xb gives us a value of, we're expecting it to be positive, otherwise there wouldn't be a root there probably, is 4.625. 4.65. So already we can put some points in our graph and show that this is minus 1.625, and this one's up here is plus 4.625. So maybe our function is going to go through these points something a bit like that. I don't know, we might have to redraw that in a minute when we've got some new points. So here we go, we've done all the preparation work. Now we can get into the iterative method of the bisection method. So step 1, find the midpoint. What's halfway between 0.5 and 1.5? Well, that's clearly just 1. So we've got, we'll do this in orange, x1 equals 1. Therefore, we've got this. F of x1 equals, so we've got minus 3 times 1 cubed plus 7 times 1 squared, so that's plus 4, plus 2 times 1, so that's plus 6, minus 4 is plus 2. So f of x1 equals 2, which is positive, of course. So that's a positive number. So when we cut this domain in half, which is about here at 1, we've got a positive number, which looks about right for our nice guessed graph. Okay, so it's up here and it's a positive number. So we'll come to number 3, which is it good enough? Can we stop? And let's say, no, we can't stop yet. So we're going to have to do step number 4, which is choosing our new domain. So we've currently got xa being negative, xb being positive, as we expect, so down here and up here, and our point between x1 is equal to 2, so it's between the two, and because it's positive, that means that we can exclude xb because they're both positive. We suspect our root will be between xa and x1 because of that sign change. So we now are looking for x2, and it's going to be the midpoint between 0.5 and 1, which is, of course, 0.75. So we evaluate the function at 0.75. F of x2 equals. So we chuck in the numbers, and we find that the answer is 0.172. 0.172. Okay? And that is a positive number, positive here. So we've gone to this midpoint here, which I'm going to have to, well, looks like we're going to have to remove our guess function because it's not been good enough. And it's positive again. It's very small, but it's positive, so it's up here, right? We can chuck in a new guess function. Why not? Okay, it's going to look something like this. Okay, so this new value, which is at 0.75, 0.75, was positive again, up here, positive. So, is it good enough for us to stop? No, it's not yet. We have to choose a new domain. So the new domain we're going to choose has to be, so 0.5 was negative, at 0.75 it was positive, and at 1 it was positive, so we're going to have to exclude 1. So our new domain is between xa and x2, and halfway between xa and x2 is the point x3, which is going to be 0.625, 0.625. Okay? If we evaluate the function at this point, at x3, we get minus 0.748, okay, which is a negative number. So we've gone halfway between these 2 points, and we come down here, and we find a negative number, okay? Is it good enough net? No, we'll do one more iteration. So we look at this function, and we found that x3 was negative, so our function's gone negative, negative, positive, so we exclude the first point, which was xa. So we're now looking for x4, which is halfway between x3 and x2, which is, of course, 0.6875. That's the one, 6875. So f of x4 equals minus 0.291, which is a negative number. So this point here, but that's already getting pretty close to 0. So we're going to stop there, right? We have decided that this value is close enough to 0 that we pretty much know where our root is. So using 4 iterations, we started off with a domain of uncertainty of our root's location that was 1 wide. But now we know that it's between our two values 0.6875 and 0.75. So it's from 0.6875 up to 0.75, which is a much, much smaller range of uncertainty. And that has allowed us to then say, okay, for a start, we can be confident that our root is in that interval. And for a second, we can say that if we chose to evaluate our root at this point here, we'd only be that far away from 0. So that's a very basic introduction to the bisection method, just showing you 4 iterations. I hope you can see that if you program that into a computer, that's a very simple and not very labor-intensive way of finding roots, and you could very quickly head towards them. What I'm just going to quickly show you before we finish is 4, or I think possibly 3 things to look out for, 3 potential problems that you might run into when using this method. So the first one is that just because you've got a sign change does not mean that you've got a root. Okay, so if we imagine the function f of x equals 1 over x, it looks like this. Okay, so if someone gave you, without giving you the function, if someone gave you these 2 points, one here, that's a negative point, so this is xa, and another one xb over here, this is positive, yes, you've got a sign change, but what you've got instead of a root is an asymptote along the y-axis here. So if you proceeded with the bisection method, you would find this asymptote, but don't be fooled into thinking it's a root. Okay, and you'll see that when you evaluate the function, the numbers will get extremely large. So the next thing to look out for is if you've got a turning point. So if your root is also a turning point, so for example on the function y equals x squared, so we'll put this one back up here. So here's the example of the asymptote. The next one, if you've got the function y equals x squared, it's classic parabola, where the parabola touches the axis exactly at 0. And the way you can think of this is that it has 2 coincident roots. So it's got 2 roots that fall in exactly the same location, which is, of course, the point 0, 0. And so although you know that this function does touch the x-axis, any points either side of it are always both going to be positive. So although you thought you might have a function that you can investigate, actually the bisection method wouldn't let you be able to find this point on the graph. And the third thing to look out for, so this is the function f of x equals x squared. And the last one to look out for is when you've got 3 roots all very close together, or an odd number of roots all very close together. So if I had a function that looks like this, it came up and just wiggle either side, you might not notice, especially if you were doing this with computational methods, and you've just been given this sort of black box function which spits out a graph like this, you might not have noticed that it flips either side of the axis. So if someone gave you your starting points here, xa, and here, xb, you might have thought that there was just one root between them, because you can see that this is negative down here and this is positive up here. What will happen is, as you pursue the bisection method, so as you go through these 4 steps, you will chop it in half first, and maybe you'll land between 2 of the roots. Okay? What you'll have to do is, as you proceed with the method, you really will end up with one root. You will find a root by doing this, but you might still have 2 others next to it that you haven't seen, or an even number of others next to it that you haven't been able to spot. And so what you're going to have to do is think carefully once you've found that root and investigate slightly either side of the root and see if there are more roots to be had. Okay, so those are the three things to look out for. Things with asymptotes, things with coincident roots, and things with multiple roots all very close together. Okay?